Hello and welcome. So today our first algorithm will be binary exponentiation algorithm. So we will see that we have pretty much algorithms that we will at each time we'll have to either come up with some algorithms, do some new ones, or do some variations. And I wanted you to know that you can always access my code, the source code in here in my GitHub profile / YouTube, and here you can come to algorithmic training, and you can find all the code that is to that you will see actually in those videos in here in let's say in Jupyter notebooks. Oh, they are all available in there. So let's get going with our first algorithm and our first concepts. So here we want to make some binary exponentiation. So what does it mean in here is that we want to calculate the power a or at the power of n. And in order to do that, like the traditional way, the naive approach we would say is to multiply a n times, and it's like O of n. It's a total of n. So in this kind of advanced Python or advanced algorithms, it's better for you to have some previous knowledge of what is O of n and what are those concepts. If you know them, that's totally fine. If you don't know them, you can keep up, and I will try to explain them, or you can ask. You can also learn about them, but mostly tot of n and tau of log of n is like the time it needs to be executed. And here, when we say tau of n, is this naive approach would need n times, like n executions, or n, let's say n execution of this instruction a multiply a multiply a n time. And here we can see that if we do the binary exponentiation, it will allow us to calculate this a power of n in a log n time. And this will do it with this associativity rule, and we will do it in a way. Here we will describe the algorithm, and we will do it in a way, instead of doing as we have seen in the naive approach, a multiply a n times, would do it in another way, since this associativity rule gives us this kind of writing of power, like a power b plus c equal a power b times a power c. So we can say that, okay, if a is power 2b, then then it's equal to a power b times a power b, and it's a power b, all of it at the power of 2. And this is quite interesting, because this can give us the opportunity to make this calculation at a tau of log n, because we'll just need to calculate just a of at the power of b and multiply both of them, instead of keeping multiplying n minus 1 times. We'll multiply each time till the half of the n, and we'll see it later on. And there is another example of this idea, is actually to take this, let's say 13, we will convert it to a binary. So I would encourage you also to check out what are binary numbers and how we do this kind of conversions. If you're fine with it, that's totally fine. If not, here we can just write this 13 in another base. Here is in the base of 10, and here we can write it in the base of 2. and here you can see that actually all those bits are where we set the power of 2, and here we see that 3 power 1, and we have 3 power 2 is not in here because the 2 here is set to 0, so we won't have 3 power 2, we'll have 3 power 4, and we will have 3 power 8. So those are just 2 times power 1, 2 times 2 power 0, 2 power 1, 2 power 2, and 2 power 3. And the 2 power 1 is not in here because this this bit we say is set to 0. So just the ones that are set to 1 are quite displayed. And this kind of exponentiation, this is the binary exponentiation. This is how we will actually be able to calculate this power of a in a log of n time, or log 2 of n, or log of n time. And this also can be shown as well here. So if we have 3 power 1, it's 3 power 2 is 3 power 1, the all power 2, and is 3 power 2. So, and here we can calculate the previous the next let's say the next power with the previous one. So 3 power 2 all power 2, it's 9 power 2, and it's 81. We had 9, we power it to 2. We do just one multiplication because we have the both values, and we have 81, and this 81 will plug it in the other one, and we will just let's say exponentiate it 2 times, and it's just like a multiplication. It will be just one operation, it's just 81 times 81, and not some bigger operation like 3 power 8 would be like 3 times 3 times 3 times 3 times 3. And here we can see that this is the same way. This is the same way we have calculated this 3 power 13. We just have put in those values, and we have calculated them, and we have found our value. So the logic behind it is that if you want to calculate a power n in a recursive approach, that's what we will do, is that if n equal to 0, it's 1. If this is our stopping condition for the recursive approach, if n greater than 0 and n even, so a would be where power n would equal to a power n by 2, the whole power of 2. So here we can see that this is actually a power of n, because if we do this one times the a n times a power n by 2 would be just a power of n. Just we have changed, but it's basically our number. And here we can really see that we are not calculating the let's say the products till a power n, but we're stopping already at n times 2, and it's an immense efficiency trade-off here, and we can see it from n to log n. And here if n is odd, then we would just say, okay, we will stop at the n minus 1. We stop at n minus 1 by 2. And because n is odd, n minus 1 would be even. N minus 1 by 2a, the whole of 2 would be just a power n minus 1. So a power n minus 1 times a would be just a power n. So we just have changed from this, let's say, this base form to a more associative form, to a form like this, with applying the rule of associativity. So till here we didn't really use much of this bit manipulation, but we'll get to it. here we can have a first recursive approach that will just use this function. So we would have the bin power of a b. So if b equal to 0, we'll return 1. This is our first stopping condition. We calculate the result and we say, okay, the result is binary power of a b by 2, and this is the floor the integer division. So we have really to do the integer division here. We each time we have to divide this n by 2, and we calculate the power of a by n by 2, and this is n, like this b is n. So if b is modulo 2, actually what does it mean if b modulo 2? B modulo 2, if b is even, so b modulo 2 would be 0. So if it's even, this would be false. 0 is false, so it will go to this else. So here, if b is even, if b is even, it will return res times res. So what is results times results is the bin power of a times bin power of a by b by 2, and it's this results we have here. It's exactly we have in this one here, and the same goes for this one. For if b is odd, so b modulo 2 will be 1, and this will be evaluated to true, and it will give us the results, these results times the same results, since we have the result from the binary power, and it will be times a. So this is our results, this one. So let's see what will it give us. Here we have some let's say some timing just to calculate, and there we can see that actually let's see, so here we'll just calculate the power of 3 1 3 2 3 3, and we have our let's say our value in here. Next would be the approach based on the binary approach, and here we will do something, the recursive approach just based on the binary. So we say while we have the b is we start the results as 0. So if b is greater than 0, well, b if is not greater than 0, we will have results equal to 1, and we will have 1 for the initial condition. If b and 1, so this is a binary operation between b and 1. So if b and 1, it evaluates to 1, so we return the results equal results times 1. So we will see what is this result. And here we see that we have an a, and here we're not having really a recursive approach anyway. It's just a normal approach. So here the result is this one, actually this one equal to 1, and if b and 1, like if b is not null, actually let's say 1 and 1 would be 1, or 2 and 1 would be 1. Okay, no, 3 okay, no, sorry, it's like more no, 2 and 1 wouldn't evaluate. Actually, if b and 1, it's more for evaluating if it's even or odd. So if we see here, like this 0 and 1, it's even, 1 and 1, it's odd, 2 and 1, it's even, 3 and 1 it's odd, and 4 and 1 is it's even. So here this one, like it's basically just like b modulo 2, and we evaluate it, and this time we do it in a bitwise. As you see here, if b and 1, let's say b and 1, it's an odd number, so we say, okay, result equal to result times a. So we start to have our first a. Here it started at 1, and here when it's odd we get our first a. And a, we say, okay, now we have a equal to a times a. So now we do this multiplication. Since we are dealing with powers, we'll do some multiplication. Once we have done this multiplication, a by a, the result is alone, and here we have our a. We're re-evaluating and reaffecting a new value to a. So we have the square of a into a. The result is already a in the first iteration, and here where it is also interesting, so we have a shift. So here we used let's say a byte operation that is like a modulo, like I will maybe tell you like why like I think to cover explicit base, why should be able okay, there is a binary conversion in Python, just to let you know like what's happening, like this is 2 and this is 1, and that's why these 2 and 1 they evaluate to 0, because 0 and 1 is 0 and 1 and 0 are 0. And if we do it with 3, this is 3, so 3 and 1 are actually 1. Okay, 3 and 1 are actually 1 because you would have this one here. Forward here, there is the second one is the logical shift. So this is very important because here b we shifted with the 1, and we are really basically doing what's kind of happening in here and what's kind of also happening in here, because here this b, when we do a logical shift, when you do a shift, it's like b you divide it by 2 actually. You take your 13, you started with 13, and if we shift 13 with 1, it will give us 6. It's like our logical our integer division of earlier, if you say by 2. So this is actually equal 13 shift 1. So it evaluates to 2. So that's what's happening in here. So we're doing it, we really, since we are having a binary exponentiation, treating this as, let's say, a normal binary operation, or a binary in the base of, like here in the decimal base or here in the binary base, it's totally the same. And also here you can also use the knowledge of the binary operations already. So that's what's happening here. We just divide b by 2, and here we just having we divide it by 2, and we are still, if it's still b is still more than greater than 0, we'll do our operation, and we will just continue till b equal to 0, and we'll return the result. And here definitely it will work, because we just followed the same logic and we did it in a non-recursive approach. We could do the same here, just now we have a recursive and a non-recursive one. So if we try it, it does definitely work. And the good thing is it can work really with very big numbers very, very fast. If we if we try to do it with let's say a normal method, it can take some time. Like let's say I in range 100,000, say a equal 3, so a times equal 3, yeah, times equal a, and here we have start, and then here we can just comment this line or just get rid of it, and here we can really yeah, maybe print a. So here it took here it will take some really good time. So this is the normal approach, and it will take 100,000 times. Here it took just log of 100,000, which is just basically 100,000, which is really not something amazing. So we need the binary log. This is by 10, the log by 10. So here it takes like, yeah, here it just fabs out the 10,000 iterations to 100,000 let's say operations to just 16,000, and there we can see 100,000 is really still running. So we can just terminate it. I would leave it for later if you want. So here we have also some other applications if you want some effective computation of large exponents modulo. There is an exercise we're gonna do it, an algorithm as well. We're gonna do it on it, and actually to compute this xn modulo m, it's a very common operation, and for instance we will use it, blah, 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 and the solution is really to embed this kind of modulo in the let's say in the multiplication. I can let you try this by yourself, because we're gonna do an exercise on it as well. Also some other applications, you can also have some effective computation of Fibonacci numbers, and because to calculate Fibonacci numbers, we have also an exercise on it. To calculate Fibonacci numbers, there is a way of doing it by calculating, so just a little intro to Fibonacci numbers if you don't know them. Just you can calculate the third term by a combination of both previous terms. To calculate the nth term, we can do that, this fn, like you can do it by raising this. There is a matrix that is describing this transformation, and it can be, it's like with fi plus 1, fi plus 1, fi plus 2, like the whole matrix. Let's see if here's the matrix, if I can have it here. I guess I don't. Yeah, this one. So this is kind of the matrix that is kind of helping us to find this fn, and this fn we can find it by raising this kind of matrix to the nth power, so we can have a look at it. So this can be useful also in this way to make us, instead of computing all those very complicated, as you have seen, let's say loops to find the power, we can just raise it with this power with log n time. We can also apply it to permutations, a permutation k times. Applying like a permutation k times, you want to apply it k times. This can be really expensive as well, and we can solve it by raising the permutation to the kth power using binary exponentiation, and then apply it to the sequence. It can be also interesting to use this kind of algorithm. So this is what we're doing. We're understanding some algorithms that we can apply in some cases. Also, we can also apply it to a set of geometric operation to a set of points. So let's say given we have a problem, given n points, apply m transformation to each of those points. Each transformation can be a shift, a scaling, or a rotation around a given axis by a given angle. There is also a loop operation which applies a given list of transformation k times. Loop operations can be nested, blah, 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 blah. And here the solution, we can have different transformations. We can just represent them as linear operation of the coordinates. Those can be written as a 4-4 matrix, and here we have some multiplication of the axis by those transformations. And here we just have the matrix of the transformations, and applying those transformations n times is to raise this matrix to the power of this k or of this n. And we can use this binary exponentiation. So it comes in very, very handy. So also we have the number of paths of length k in a graph. So given a directed unweighted graph of n vertices, find the number of paths of length k from any vertex u to any other vertex. So we have a graph. We'll get to see we have some graphs up here. Maybe graph. I think it will be in here. IPNB. And here we can check this article if you want. And here we have some problem is concerned more in detail in this article. We'll check the article. Algorithm consists of raising the adjacency matrix M of the graph for the matrix where mij equal 1 if there is an edge from I to G or 0 otherwise. So this is how we represent also graphs. We do this adjacency matrix. We'll check it out some time. Of course, if you stay with me. So there is some operations. We check some funny things about graphs. So here is, in order to do that, is to raise to the kth power. Now mij is the number of paths, blah blah blah. So yes, we can actually use this this algorithm to compute the number of paths of length k in that graph. Variations of binary exponentiation would be multiplying two numbers modulo m. So this is what we have, I guess. Modulo m. It's kind of what we have done in that example with modulo m. If you wanted to check it out. So this is basically it, and there are other problems that I also link in my YouTube, let's say notebooks. You can find all those notebooks just in here. So I thank you for watching, and see you for the next algorithm. Bye bye.